It is section 4.2, Newton's method. The Newton's method is an iterative method to solve the unconstrained optimization problem when the function is twice differentiable. The method can be derived by using the surrogate minimization. Let's begin with quadratic surrogate function of the form. Here Cn is a constant, Gn is a vector, and Hn is an invertible matrix. Now, start with this surrogate function. We impose conditions. A reasonable condition for the surrogate function is that at xn, it coincides with f, at least in its value and first derivatives. That means gradient. And an extra condition is now the Hn, the metric, is the Hessian of the function, so that the final form of the surrogate function is given here. Now Qnx is fxn. Now that is gradient f at xn and x minus xn, and 1 over 2 gamma, and x minus xn. Now this Hessian of f and x minus xn. This surrogate function is a local approximating function of f around xn. By minimizing this surrogate function, we try to get new update. In order to do that, because it's quadratic, we can easily do that by using calculus technique. Just differentiating and equating to 0, and we can solve for x. Then the x is now new update, new iterate, and if we do solve for x, then you can reach that formula. For this surrogate function, when gamma is 1, then along with the gamma 1 here, the Qn, the surrogate function, is the second order approximation of the objective function f dr xn. So when you are running Newton's method, you may choose gamma is 1 in many cases. Okay, here, where applicable, Newton's method converges much faster than the gradient descent method. As a matter of fact, and every local minimum has a neighborhood such that if we start with this neighborhood, which means that x0 is chosen from the neighborhood, then Newton's method with step size gamma is 1 converges quadratically, and assuming the Hessian is invertible and this is continuous. The convergence, quadratic convergence, means that once the error from xn is 10 to minus 2, for example, then the error from xn plus 1 will be 10 to minus 4, and for next iterate, now the error will be 10 to minus 8, and now for next iterate, the error will be 10 to minus 16, and so on. So that once the iterate is near around the local minimum, then it's converging very rapidly. The Newton method can be seen as to find the critical point. That means that try to find x hat such that gradient of f at x hat equals 0. Okay, let's see the detail. Now xn is now xn plus 1 is xn plus delta x, and with the gradient of f at xn plus 1 is same as this one, and now we make a Taylor expansion of the first order. Originally gradient is now here, the original function is gradient f, that is a first order derivative, and that is a second order term. Ignoring this portion and equating this term to 0. Okay, let's ignore this second order term, assuming delta x is small, and then we try to equating this term to 0 and solve for delta x, then you can reach that one. So that is exactly the Newton's method. Okay, we have here implementation of Newton's method. And the Newton's method is almost same as gradient method. The difference is now appearance of that Hessian inverse. And we thought this one is the same as the gradient method. Okay, it's now that one may be expensive. Getting Hessian is expensive, and the finding its inverse is also expensive. But this is formulation of the Newton method. Okay, here we have examples. Now, for well-conditioned quadratic, one iteration is enough to reach at the minimum when we are running the method with gamma is 1. Even poorly conditioned, once it's quadratic, then also, again, one iteration will locate the minimum. Of course, here, again, gamma must be 1. Now, finally, there's non-convex function, and here we have a bit of the stability issue because oscillatory. However, this performance is better than that of gradient descent method. So once it is applicable, then it's better. The thing is, now once the dimension is very large, then and here and D is very large, and this metric is D by D metric, and so that computation of this Hessian is not trivial, and also the computation of this inverse is also here expensive, so that and number of iteration is smaller than gradient method. However, probably it can be much more, this Newton's method can be much more expensive when this portion is expensive. Okay, we'll continue this section in part 2. Thank you.